In this video, we're going to go over the review sheet for test 3, which is on unit 2, congruent figures. In number 1, we have triangle ABC, where triangle ACE is congruent to triangle ABD. So here's triangle ACE. Highlighters are really helpful. And here's triangle ABD. And we need to figure out if these two triangles are congruent, which statement's true. So since the two triangles are congruent, we're going to think CPCTC, which says that if two triangles are congruent, their corresponding parts, their corresponding sides, as well as their corresponding angles are also congruent to each other. So we need to look for angles that are in those two congruent triangles and that correspond to each other. Number 1 says angle ACF. That's right over here. And angle BCF. This angle's in the green triangle, but this one's not in the red triangle. So maybe they're congruent, but I don't know. All I know from the question is that the red and the green triangles are congruent. So I can only say for certain things that are part of those two triangles. Number 2, angle DAE is congruent to angle DFE. Those don't match up. This is not an angle of the red triangle. 1, 2, 3 angles in the red triangle. It's not an angle of the green triangle. 1, 2, 3. So this is not going to work here. BCD. BCD. Ooh, that's already too large. That's not in the green triangle. That extends past the green triangle. AEF and ADF. This is an angle in the red triangle. This is an angle in the green triangle. Let's check out that they correspond. This is also AEC. AEF is the same thing as AEC. So that's first, third, second letter. So it should match up to first, third, second letter, which is ADB, which is what we have here. So this is good. Perfect. Also, when you have overlapping triangles, a good strategy is you might want to separate those triangles. And that would make it easier to see. Let me just label them. That's C, that's A, that's E, that's A, that's D, B. And that just makes it easier to see that those two angles do in fact correspond. In number 2, we are told that we have a parallelogram. We know a lot of stuff about parallelograms. We know that opposite sides are congruent. We know opposite sides are parallel. And we also know that opposite angles are congruent to each other if we have a parallelogram. They do also tell us that DE is congruent to BF. Here's DE. Here's BF. We need to figure out how triangle EGC can be proven to be congruent to triangle FGA. Well, already we do know, since we have a parallelogram, that opposite sides of a parallelogram are congruent. So we know that, for example, AB and DC are congruent. And we know that DE and FB are congruent. So if we start with these two congruent pieces and we take away the pieces that we don't need, FB and DE, which are also congruent, we'll be left over with EC and AF, which are sides of the triangles that we need to prove congruent. So that'd be really helpful to us. So once again, we can start with the longer segments that we know are congruent because they're opposite sides of a parallelogram. We can subtract off the pieces that we don't need, which are also congruent to each other, and be left over with the sides of the actual triangles, EC and AF. I also see vertical angles. Anytime we see that letter X, remember intersecting lines form congruent vertical angles. And finally, not only do I know that opposite sides of a parallelogram are congruent, but I also know that they're parallel. So I'm going to think parallel lines cut by a transversal. And I do see a letter Z, which tells me that we have congruent alternate interior angles. I'm seeing angle, angle, side, angle, angle, side. If you read it the other way, side, angle, angle, that's the same thing as AAS. We could eliminate AAA right off the bat. That does not work to prove triangles congruent. We could also eliminate this. This does not work to prove triangles congruent. This is a bad word if you read it backwards. And we didn't have right triangles here, so we actually could have eliminated everything. In number 1, this is a right angle, so this has to be a right angle because they form a linear pair. 90 plus 90 makes 180. And then we have a shared side due to the reflexive property. So we do have side, angle, side, side, angle, side. Here, we do have congruent vertical angles. So we have angle, angle, side, angle, angle, side. Here, we do have a shared side between the two triangles. So it's congruent to itself by reflexive. So we have side, 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 side. Here, we have SSA, or if we read it the other way, ASS. SSA, which is ASS, does not work. This is the choice we're looking for, the one that doesn't prove two triangles to be congruent. Whenever they're talking about a triangle and you don't see a diagram, just draw your own. It's triangle ABC. AB is congruent to AC. A is 3x, and angle B is x plus 20. When we have a triangle that has two congruent sides, remember the opposite angles are congruent. So here's one side. Here's the angle opposite from it. Here's another side. Here's the angle opposite from it. So these two angles are the congruent ones. So I'll label this one as x plus 20. And now that we've labeled these triangles, we can now find the value of x. Because if we take all the angles of any triangle and we add them together, we should get 180 degrees. Let me make sure I added these numbers correctly so far. That seems good to go. And we have x is equal to 28 when we divide by 5. Okay, so we're given AC is congruent to ED. And we need to end up with the fact that AD is congruent to EC. So I already see that I'm going from smaller to larger segments. So I already know it's addition. So I'm going to knock out 2 and 4. To figure out the rest, let's write out what we're going to be adding here. So we're starting with AC and ED. And our goal is to end up with AD congruent to CE or EC. Sorry, I wrote that backwards. So let's think about what we're adding to each one. To AC, we're adding CD to make it into AD. Because if we add CD to AC, we make the whole segment AD. to ED, if we add on DC, so let me write this down, plus CD plus DC. Then we get the full segment EC. So we started with two congruent segments. We were told they were congruent in the givens, but we have to be adding two congruent segments as well. Let me fix that. It just says D. That should be DC. So we do have to know that CD and DC are congruent in order to add them, because we have to start with congruent and add congruent in order to make sure our sums are congruent. Now, CD and DC are the same segment, so they're congruent to each other by the reflexive property. And we do need to say that first in order for our addition to be valid, since we do need to be starting with congruent and adding congruent. So we see here that the correct answer is reflexive property and addition. For number 6, we just need to mark the diagram with the given information. So AB is congruent to AD. BE is congruent to ED. EC is congruent to DC. Angle BCA is congruent to angle DCA. Angle AED is congruent to angle BEA. BEA. I'll just put 2 markings to make them different from these ones. And angle CDE, I'll just use a different color, it's getting messy, is congruent to angle EBC. For this next one, we need to explain if or if not ABC is congruent to triangle RST. The triangles, those should have triangle symbols. And we need to use the properties of rigid motions to explain our reasoning. So if we can find a rigid motion that maps one onto the other, then that will tell us that the triangles are in fact congruent. I want to try to be as specific as possible when describing the sequence of rigid motions. And personally, I like reflections, so I'm going to try not to do rotations here if I don't have to. So A needs to match onto R, B needs to match onto S, and C needs to match onto T. So if I reflect it, let's see what happens. Let's reflect over AC. Because all I want to do is get the orientation the same way. So to reflect over line AC, the only point that's going to move is B, because A and C are already on the line of reflection. So we're just going to take B and count how many spaces it is to C, and then move an equal number of spaces on the other side of the line. And right now the orientation looks good. A matches up to R, C matches up to T, and B matches up to S. Now we just need to check out if we can land them on top of each other. But actually, the orientation's still not good. Right? It'll need to be turned a little bit still. And actually, if you also take a look, the length of BC, because I just traced it over here, is longer. So it looks like these triangles are different sizes. So the triangles are not congruent because there is no rigid motion that could take you from this one to this one. So I'm going to put that over here. The sizes are different. So there is no rigid motion that will map one triangle onto the other. So the triangles are not congruent. Okay, over here, we're told that ABCD is parallel to EHK. And we're also told that BC is congruent to BH. So automatically I see a triangle with two congruent sides. So I know that the angles opposite from those sides are congruent as well. Angle NCD is 62 degrees. We need to find the measure of angle PHK. So we're looking for this angle here. And we do need to explain in words how we got our answer. So anything we mark in the diagram has to be explained in our explanation, else we will not receive credit for it. What I noticed first is that these are vertical angles. So that's 62 as well. And that means this one has to be 62 also. I also know this that with the parallel lines cut by the transversal, that, let me highlight it this way instead, with this transversal. We could see the letter Z. So I know in the corner of the Z's, we have alternate interior angles that are congruent. This is 62 and this is 62. So together that makes 124. And then all three angles of a triangle make 180 degrees. So to find the last angle, if we do 180 minus 24, we can find the last angle of the triangle. So let me do that on my calculator. And I got 56 degrees. So that's 56. So we have 56 as well. And these are vertical angles. So the angle that we're looking for is 56 degrees also. Let me write this down in words, and I want to make sure that everything we put in the diagram makes its way into the explanation in order to get credit. Since BC was given as congruent to BH, angle BCD equals angle BHC, since angles opposite congruent sides are congruent in a triangle. Triangle, I can't spell tonight. And that is the base angle theorem, or the isosceles triangle theorem. Since angle NCD and angle this angle is BCH, not BCD. BCH. Since angle NCD and angle BCH are vertical angles, they are congruent. So angle BCH and angle BHC are 62 degrees. Since ABCD is parallel to EHK, alternate interior angles CBH and BHE are congruent. All angles of a triangle sum to 180 degrees. So angle CBH is 56 degrees. And we showed the calculations for that over here. Meaning that angle BHE is also 56 degrees. Since angle BHE and angle PHK are vertical angles and are congruent, angle PHK is also 56 degrees. Once again, the only thing that you get graded on for an explanation question is what makes it into your explanation in words. Over here we have a proof. So don't look at the proof yet. I just wrote it up, but we're going to mark the diagram and talk about the components. We have AE is parallel to DF. We have EB is parallel to FC. And we're also told that AC is congruent to DB. Let's take a look at the parallel lines first. I'm going to start with the blue lines. Notice that letter Z. So we have in the corners those congruent alternate interior angles. So that's right here, angle EAB, and right here, angle FDC. So that's step 2 of the proof. You'll see that I stated that these angles are congruent, and I put my complete reason why. Alternate interior angles are congruent when parallel lines are cut by a transversal. you have that what you're subtracting is congruent so that your differences remain congruent. So if I'm subtracting CB and BC, I have to know that these are equal to each other. And of course, CB is the same segment as BC. They're the same. So we need to justify that using the reflexive property in order to make our subtraction valid. In this next proof over here, we have parallelogram FLSH, and they tell us G is perpendicular to FS and HA is perpendicular to FS. Now, I know here they put the little boxes to indicate the right angles inside the diagram, but let's not let that trick us. The right angles still need to be mentioned in the proof because it was not part of our given information that we had right angles. The only thing that was given was that we have perpendicular lines. So notice how the start of my proof after the givens, so that I don't forget it, is I put down that the two angles marked with the boxes, angle LGA and angle HAF, are right angles due to the fact that perpendicular lines form right angles. And then I did say that they are congruent to each other because all right angles are congruent to each other. And that gives us a pair of congruent angles to work with. Now, in order to know what's important here, I do recommend taking a look at the proof statement. We're proving that GS, where's GS? Right over here, is congruent to AF. Where's AF? Let me get it in a different color. Right here. Oops. Right here. So one of the triangles that we're working with is this triangle because it has AF as its side. And the other triangle that we're working with is this triangle because it has GS as its side. And we know that if we want to prove corresponding sides of two triangles to be congruent, then that's going to be CPCTC. And before we can use CPCTC, we do first need to prove that these two triangles are congruent. So from the right angles, we already have a pair of angles to work with. The rest of the information is going to come from knowing that we have a parallelogram. To the fact that we have a parallelogram, we know that opposite sides of the parallelogram are congruent. So that gives us LS equals to FH is congruent to FH. We also know that opposite sides of the parallelogram are parallel. And then you guys can see that we have a letter Z. So what we do have are those congruent alternate interior angles. And now we have enough information to prove the triangle's congruent. We have angle, angle, side. You can take a look at how this is written up over here. We're going to move down over here to the last proof. So the reason why this proof is tricky is because the triangles are overlapping. So when you have overlapping triangles, a really good idea is to take the triangles and draw them separately. And that way, when I mark the givens in the diagram, I'm also going to mark them in the separated triangles. Oh, and it looks like I didn't even finish this proof over here because our ultimate goal is to prove angle B congruent to angle E. B and E are corresponding angles of the two triangles. So in order to ultimately prove that angle B is congruent to angle E, this is going to be another CPCTC proof to show that corresponding angles of two triangles are congruent. And in order to use CPCTC, we do first need to show that the triangles are congruent. So the goal as we go through is to get the information to prove these two triangles congruent to each other. These are the triangles that have angle B and angle E as angles, and that's our focus. So first we have that DG is congruent to CG. That is not visible on the separated triangles. So if I look at the original diagram, I notice that this inner triangle formed by like the overlap of the two larger triangles, this inner triangle has two equal sides. And that means it has two equal angles. That gives us angle EDF congruent to angle BCA. And that gives us a pair of angles in the two triangles that we're interested in. Notice how it's really much easier to see where those angles are located when we separate the triangles. When you have overlapping triangles, separating the triangles is the way to go. Okay, next they tell us that AD is congruent to FC. So AD is not the full side of the triangle. AC is the full side. And FC is not the full side. FD is the full side. So we have information that's too short. In order to make it longer, we can add. Let's take a look at what we'll be adding. To AD, we're going to add DC to make AC. And to FC, we're going to add CD to make FD. So notice how to AD and FC, we were adding the same segment. So in order to add, we need to start with congruent and be adding on congruent. So in our proof, we do need to say that DC, the segment that we're adding on to AD and also to CF, is congruent to itself by the reflexive property. And that will make our addition valid so that we can prove the triangle's congruent. So that gives us AC congruent to DF. And our last piece of given information was that BC is congruent to ED. So what we have here is side angle side, proving the two triangles congruent to each other.